Now I will come to certain important understandings, some important understanding of the strength and toughness of solid shell. I have mentioned that during solidification solid shell has started forming. It has become 100% solid at the end of solidification, and then we have only solid, but the toughness and strength at different temperatures we have to be very careful about it. Now let us see what is happening during solidification. Here I will give the concept of ZST, means zero strength temperature. Some people call it NST also, that means nil strength temperature. That means at temperature during casting where the strength is first evolving. The strand initially you have totally liquid and solidification is starting at the meniscus level. As you are going down the continuous caster, the solid shell is increasing in thickness, but still there is liquid. So it is the strand which is important. So in the solidifying shell or the strand, what is the temperature at what is the temperature when the strength is first evolving? What is the temperature when the ductility of the strand is first evolving? In liquid there is no strength, in liquid there is no ductility, but at what stage of solidification this strength and ductility are emerging or evolving, that is important. Let us try to understand from this figure what is happening. These are the dendrites which form during solidification. So what is happening, look at here, this is the liquidus temperature, that means solidification is starting at this point, at this temperature. So this is liquidus TL, solid fraction F is 0. So as you are going down the caster, so the solid shell is increasing slowly. So we have dendrites, so this area is basically the liquid plus solid zone, because you have dendrites solid, you have liquid also. So at this particular temperature you find total solidification is complete, that means Fs equal to 1. So solidification is starting at liquidus temperature, solidification is complete at TSA, that means actual solidus temperature, so Fs equal to 1. So that means this is the range of temperature for solidification, TL to TSA. So now it has been found that when the solid fraction is around 0.7, that means you have 70% solid, 30% liquid. In that mushy zone, in that area of mushy zone, the strand has started developing some strength. When the solid fraction is less than 0.7, some people tell this is 0.7, some people tell this is 0.75 solid fraction when strength is evolving. But what is important to understand is that before solidification is completing, the strand has started developing strength. So when the solid is 70% or 75%, the strand which has the remaining amount of liquid, that means maybe 25% or 30% is liquid, so that strand has started developing strength. But what is important is that it has no ductility at that particular point of time. Ductility is 0 when the solidus, actual solidus temperature is reached. That means at the point of complete solidification, when Fs is equal to 1, solid fraction is 1, that means when solidification has just completed, that temperature, what is that temperature? It is the actual solidus temperature, we call it TSA. So this TSA is more or less equal to the ZDT temperature, it means 0 ductility temperature, nil ductility temperature, because only at this temperature the strand starts developing ductility or toughness. So this is important, look at this figure of ductility, and this dotted line is the figure of strength in the strand. So when the solid shell is less than 0.7, that means when the solidification has started and up to say about 70% of solidification is over, that means the solid is 70%, 30% is liquid, there is neither strength nor ductility in the strand. When the solid fraction has reached 0.7 or say 0.75, the strand has started developing strength. So, ZST, that means the 0 strength temperature, on NST, the nil strength temperature, is more or less the temperature at which the solid fraction is 0.7 or 0.75. So, here strength is developing. Less than that, there is 0 strength. Strength is started developing. So, at this temperature region between ZDT and ZST, that means between solid fraction of 0.7 to solid fraction of 1, what is the situation? The strand has strength, but the strand does not have ductility. Ductility is starting to develop only at the completion of the solidification at ZDT temperature, that means at TSA temperature, actual solidus temperature. So, in this temperature interval, it is very interesting to know that this dendrites and the whole strand, it has some strength, but it does not have toughness. So, what is the situation like? A material which has strength but no ductility or toughness. So, it is very brittle, it is like glass. So, it is very dangerous to handle such material. So, we have to be very careful about this material, because there is a possibility of even small strain, small force causing crack in this material when the solidification is more than 70%, but it is yet to be over. So, this temperature zone is really a matter of worry, but fortunately for us, suppose because of the low toughness, some crack formation takes place at this surface. These dendrites, these zones, solid zones, are relatively, why relatively? There is no toughness at all, but it has some strength. So, what is happening is, if due to some strain, external strain or internal strain, whatever might be the source of the strain, because of any force which is interacting with this dendrite, so there is a possibility of crack formation. If the crack formation takes place on the surface, then what happens? The liquid steel will heal those cracks. So, the possibility of crack continuing, sustaining is not there till this region, when two dendrites are touching each other. When the two dendrites are touching each other, solidification is not yet complete, but liquid cannot penetrate in this region. Look at this. So, this normally this is around 90% of solid fraction. That means, when the 90% of solidification is complete, till that time there is enough liquid by the side of the dendrites, in the periphery of the dendrites, which can heal up the cracks which can form because of the low toughness of these dendrites. But in this region, that means when the solidification is more than 90%, in this particular region, that means in the temperature region between solid fraction of 0.9 to 1, that means near the actual solidus temperature, this temperature region is really brittle temperature region, because if there is a crack formation in the dendrites, the liquid steel cannot penetrate and heal those cracks. So, this temperature is called liquid impenetrable temperature, LIT. So, I have talked about 3 temperatures. First is the 0 strength temperature or null strength temperature, nil strength temperature, ZST or NST, which is coinciding with solid fraction of say 0.7 or 0.75 during solidification. I have talked about ZDT, that means 0 ductility temperature or nil ductility temperature. So, this is more or less coinciding with the actual solidus temperature. So, ZDT is coinciding with the TSA, actual solidus, and ZDT more or less are similar. So, this corresponds to a solid fraction of 1, that means when solidification is, actual solidification is just complete. Now, I am giving another term, LIT, liquid impenetrable temperature. This is basically the temperature corresponding to solid fraction of say about 0.9. I mean, there is some amount of difference of opinion whether it is 0.9 or 0.85 or say 0.92 or 0.87. Nevertheless, let us go ahead with this figure that when solid fraction is around 0.9, then what is happening? The dendrites are touching each other, liquid steel cannot penetrate this area. So, even if there is cracks in this area, when the solid fraction is less than 0.9, liquid steel can come to the cracks and heal those cracks, get in touch with the cracks and heal up those cracks. But in this particular zone, that means when the solid fraction is more than 0.9, so beyond 0.9, which is the liquid impenetrable temperature, this temperature region is the real brittle temperature region. So here the toughness of the dendrites is nil, but even if there is crack formation, there will be some crack formation because of this low toughness. Liquid steel go and heal those cracks, but in this temperature region, when again there is no toughness here, so there is a possibility of crack formation, but the liquid steel cannot penetrate in this region and heal up those cracks. So what is happening here? If cracks are forming, liquid steel are healing up. So even if the dendrites have zero ductility, this temperature region is relatively safe, but this temperature region is really unsafe. That means the temperature between 90% solid fraction to 100% solid fraction, this particular region here, because there is no ductility but there is strength. So if there is a crack formation due to some external strain, the liquid steel cannot penetrate and heal up, so the cracks will remain. So this temperature zone is called the brittle temperature zone or region near solidus, actual solidus. So this is, please try to remember, this is one of the important regions during solidification, because this is prone to formation of crack. So this region towards the end of the solidification is very prone to formation of solidification crack. So we have to be very careful about that. So I have mentioned here 0 strength temperature ZST corresponds to solid fraction of around 0.7. 0 ductility temperature ZDT corresponds to actual solidus temperature TSA, that means solid fraction is around 1, that is 100% solidification. That means at the end of solidification, actual solidification only, we are having 0 ductility temperature. So during solidification, the dendrites have no toughness at all, they are brittle. So only after solidification is complete, they are developing certain ductility, and it increases as the temperature goes down. But I will discuss later on that it is not very high at all temperatures. What we are showing here is just after solidification, after certain temperature, it increases to a high level and continues. But as I will show it later on, this ductility value again decreases at certain temperature range, which we will call it brittle temperature regions, which is lower to the solidus temperature. So what I am telling is, around the solidus temperature there is a brittle temperature zone. This is the temperature zone during the end of solidification. So many types of cracks will be created in those region, because this is a brittle temperature region. Whatever cracks will form in the dendrites, they cannot be healed up by the liquid steel. So the whole idea is to try to avoid this temperature region. How will you avoid this? By cooling relatively faster. You do not allow much time for the dendrites or the solid shell to remain in this temperature region. That way you can avoid this region. You do not allow them to be in this region for a large amount of time. So this is important. So I have mentioned here that the brittle temperature zone near actual solidus is between solid fraction of 0.9 to 1. That means the temperature interval between LIT and actual solidus. This is the temperature region which is brittle. We have to be careful. We try to avoid this temperature region when solidification is taking place. Otherwise, there will be crack formation which is difficult to heal, because liquid steel cannot penetrate. I think it should be clear to you by this time that though dendrites have started developing strength at around say 0.7 solid fraction, they do not have toughness. They start developing toughness only after the solidification is complete. But in the temperature region between say solid fraction of 0.9 and 0.7, this region there is no toughness, but even if the cracks form, the liquid still, sufficient liquid still is there during solidification in this temperature, in this temperature region between LIT and ZST, that means between the solid fraction of 0.7 and 0.9. So even if there are crack formation, there will be definitely crack formation, but these cracks are held up by the liquid steel, adjacent liquid steel between the dendrites. But this is not possible. Liquid steel cannot penetrate this region and heal up the cracks when LIT, that is a liquid impenetrable temperature, is reached. That means when the solid fraction is more than 0.9. So in the region between solid fraction of 0.9 and 1, even if cracks are forming, they cannot held up by the liquid steel because liquid steel cannot penetrate. Here liquid steel can penetrate and heal up the crack formation in dendrite surfaces, the dendrites, but here they cannot because they are touching each other. So liquid cannot penetrate. So this temperature region, which is near to the actual solidus temperature, is a real brittle temperature zone near actual solidus. This is called the high temperature brittle temperature zone, because this temperature is relatively high, because it is associated with the completion of the solidification. After this, the temperature will only come down because you are cooling it. So this is the high temperature zone which is brittle. High temperature zone near the actual solidus is the brittle temperature zone. So we have to keep in mind that this is a zone we have to be very careful about. Now let me try to talk about what is happening in the solid shell. What are the different forces which are operating on it? How does it behave? Because I have told you it will depend on what are the different forces or strains acting on it, whether they are acting in the same direction or different direction. If they are acting in different direction, which force is more predominant. So the behavior of the shell, solid shell, will depend on that, will be dictated by that. So two opposing forces are acting on solid shell. What are the opposing forces? I have mentioned that first and foremost is the ferrostatic force. Due to the liquid, during solidification there is liquid present in the strand. So this liquid will give ferrostatic force, will push the solid shell towards mold when it is within the mold. So what is the what is the value of that force or strain? It depends on the ferrostatic force as such. What is the strain on the solid shell which will try to push it towards the mold, or will try to bulge it when it comes out of the mold. It is this SB, if we call it the bulging strain SB, it is equal to the ferrostatic force divided by the strength of the shell into the thickness of the actual shell thickness into square. I have told you that this shell, solid shell strength is very important. This value, this is this rho is the strength of the shell. This will try to resist the force, the strain of ferrostatic force. So higher this value, thicker is the shell, more the solid shell can resist. So this the sticking or the bulging shell will depend on ferrostatic force is fixed, say it at a particular level of solidification, it goes on increasing as you are going down and down because of the additional what is that called additional force. So as you go down, the caster ferrostatic force or the overall force is increasing, but at a particular level this is fixed F. So at a particular level the sticking or bulging shell will depend on strength of the solid shell and the thickness of the solid shell. If the strength of the solid shell is low or the thickness is narrow, then it cannot withstand the force, and say there will be relatively high amount of strain in the solid shell. So, next, this is one force, sticking or bulging. Another is, I have mentioned, is the shrinkage. Now, this shrinkage is due to what? I have mentioned shrinkage can be due to solidification first and foremost. Whenever there is a solidification, there is a shrinkage. There may be a cooling. Because of cooling, I have mentioned you that the surface is relatively cool, inside is relatively hot. So, because of this temperature differential, there will be a shrinkage because of the cooling, then there will be a strain. So, this cooling, and then there is a transformation from delta Farad to gamma. Again there will be shrinkage, there is a density change, there is a shrinkage. So, this shrinkage, total shrinkage of solidification, cooling and transformation from delta to gamma, if we add all these shrinkages, then the strain due to the shrinkage, it depends on what? There are different components I have told you. That is due to solidification, there is a this thing shrinkage, there is a cooling which is a thermal one, and there is a transformation. Now, the thermal one can be found out by using the coefficient of thermal expansion beta, and TSA is the actual solidus temperature and T0 is the surface temperature. So, the temperature difference between this and the coefficient of thermal expansion, multiplication of that will indicate what is the strain. So, the thermal strain is because of this. On top of this, there may be a transformation strain, which we call it STR, is relevant only in brittle temperature zone. I have mentioned in the last transparency that in the brittle temperature zone, that means this is the brittle temperature zone between LIT and ZDT, that means between the solid fraction of 0.9 to 1. So, if in this temperature region there is a transformation from delta to gamma, then only this is effective. Here if you have a transformation, it is not effective, it will cause crack, but liquid still will heal it up. But if there is a crack formation due to too much of strain here, so that you cannot do anything, so there will be a crack formation. So, whatever strains I am talking about, if they form in this region, they are really a matter of OD, or even lower temperature is a matter of OD. So, that is why what I am mentioning is the transformation strain is relevant in brittle temperature zone between LIT and TSA, that means the solid fraction between 0.9 and 1. So, if let me try to come to a very interesting observation here. I have talked about two strains. Due to ferrostatic force, there is a sticking or bulging strain. Sticking, because when the strand is within mold, the ferrostatic force will push the shell towards the solid shell towards the mold. But when the strand is coming out of the mold, then there is no mold to support. So, what is pushing? It is pushing the solid strain and causing bulging in the secondary cooling zone. So, there is a possibility of bulging within the mold, it is sticking, beyond the mold lower, as you come down from the mold there is bulging. So, the strain of this, it depends on ferrostatic force. As you are going down, the ferrostatic force is increasing, but as you are going down, the solid shell is also increasing thickness. So, what is important is what is the level of F, what is the level of sigma, that is the strength of the shell. Here it is important, if it is delta, the strength is lower. If it is austenite solid, I am talking of the solid shell, the strength of shell, whether it is delta or gamma, is very important, because the strength will depend on that. Normally austenitic solid shell has about 5 times more strength. This, please remember this. So, the strength of the shell, if it is delta, the strength is low, if it is gamma, strength is more, and on top of that, what is important is the actual shell thickness. I have mentioned to you that the shell thickness depends on what? The actual shell thickness depends on the extent of microsegregation. If you have more microsegregation due to phosphorus or due to sulfur, then what is there? The shell thickness is lower and the mushy zone is wider. So, if the actual shell thickness is narrow, then also there is a possibility of sticking or bulging strain. So, it is a combination of strength of the shell and the thickness of the shell into square. Since this is the square is there, so this plays a predominant role, thickness. So, microsegregation, that is why is a cause of too much of microsegregation, that means too much of mushy zone, and a narrow shell thickness is a cause of high sticking and bulging strain. This is one. Another force just opposite to it, this force is trying to push the shell towards the mold, and the shrinkage due to solidification, cooling and transformation from delta ferrite to gamma, this is trying to push the shell away from the mold. Just see here, this force, ferrostatic force, is pushing the solid shell towards the mold. The direction of shrinkage, whether due to solidification, cooling or transformation, whatever may be the cause, it is trying to push the solid shell away from the mold. It is shrinking, so it is going away from the mold towards the liquid, and this one, ferrostatic force, is pushing the solid shell towards the mold, that is away from the liquid. So, these two are opposing forces, please try to remember. So, but which force is more, which strain is more will determine whether there will be sticking or bulging or there will be shrinkage. So, this is very important concept, try to understand. The certain grades, we call it, they are prone to sticking or bulging, and certain grades of steel, we call them that they are prone to shrinkage. This is because of this consideration. If the ferrostatic force is such that the sticking or bulging strain, so it depends on what? Ferrostatic force, the strength of the shell and the thickness of the shell. So, this will determine what is the bulging or sticking strain. So, if sticking strain is more than the shrinkage strain is it has two components, one is thermal and is transformation. So, two together is important. So, if SB, that means the bulging strain is more than the shrinkage strain due to thermal shrinkage as well as transformation shrinkage, then since this strain is more, that means there will be sticking inside the mold and bulging below the mold. And if the reverse happens, that means if this strain, shrinkage strain due to thermal or transformation strain, if this addition of those strains due to shrinkage is more than the strain caused by the ferrostatic force, then what is the consequence? This will result in formation of surface depression. So, the surface depression is characteristic of certain steel grades, and sticking and bulging are similarly characteristic of certain other grades of steel. So, grades of steel, why it is important? Because I have told you whether delta or gamma will form depends on the chemistry, how much will the shell thickness depends on the chemistry and depends on the microsegregation. So, these are very important. So, what is the thermal strain? This is again depends on the chemistry to certain extent. What is the delta to gamma transformation, when does it take place, whether at all it will take place, again depends on the chemistry. So, many factors are contributing to the different levels of sticking or bulging strain or the strain from the shrinkage. So, the relative values of these two strains will determine what are the sticking or depression tendency. Thank you very much.